Hi, I'm Fernando Pereira from UFMG, and today we shall talk about a technique that is ubiquitous in the design of JIT compilers. That's speculation. Speculation is a bit of a gamble. The JIT compiler observes the program, and based on these observations, decides to apply some optimization on it that makes sense if these observations are true. There are many ways to carry out observations. For instance, we can assume that the type of a variable is an integer, but then if a value is too big, we will have to recompile the program. Or we can assume that the target of a call is invariant, but then if it changes, we will have to recompile again. Perhaps the most well-known form of speculation in JIT compilers comes from the notion of an inline cache. Inline caches are used in languages that represent objects like hash tables mostly. The goal of this optimization is to avoid the cost of searching for a method in a table. In object-oriented languages, we can use virtual tables, or vtables for short, to speed up the task of finding the targets of dynamically dispatched calls. So in a language like Java or C++, the cost of finding the target of a method call is always constant, regardless of how many classes we've chained through inheritance. So each object is like a pointer to an immutable table. These entries in this table are pointers to methods and attributes. The important thing to notice is that the prefix of two of these tables, any two of them, is always the same. So all that the compiler must know is the offset from the start of the object's address to find out the target of a method. For instance, when we invoke a method eat, on object D, we check its virtual table. Regardless of the type of D, the offset of some method eat is always the same. And based on this offset, which is known at compilation time, the method is invoked. But in a dynamic language like in Python, for instance, this trick would be rather difficult to implement. Can you imagine why it's difficult to implement virtual tables in Python or Ruby or JavaScript? Python is duck-typed, meaning that as long as some object has some operation, this object can be used where that operation is expected. Like in this example, the method fill will work with an object that has the add operation. It can be a set or a number, whatever. Anything that has the add operation, the add method, will work. If we pass an object without this operation, then we will have an error at running time because the contract expected by the type hasn't been fulfilled. That's called duck typing, as I said. As long as the object has the operation, it can be used where the operation is expected. The main advantage of duck typing is reuse. We do not need to worry about types preventing us from combining different objects, for instance. Basically, if the object quacks like a duck, swims like a duck, eats like a duck, and does everything else like a duck, then this object is a duck. But if, on the other hand, we gain reuse in these languages, it becomes rather difficult to implement dynamic dispatch efficiently. How can we use a virtual table in the environment if we need the offset to a given operation to be always the same? Remember that we can have completely different classes implementing the same operations. But then there is an idea that really solves the problem. Well, sort of solves the problem. That's called an inline cache. It works like this. The first time we generate code to implement a method call, we check the target of this method call and assume that it will be recurring. Then we inline this method in the calling side with a guard to make sure that we do not invoke the wrong method by mistake. You can see an example of code that's generated on the right. There are different ways to implement inline caches. For instance, we can implement a stub for each method, which contains the inline call. Notice that thus far we have been talking about a monomorphic inline cache. The cache is good for one type only. But you can have situations in which multiple targets for the same method are possible, like in the example of numbers and sets. In this case, we can have multiple guards in the inline cache, so we can inline more than one target and still have some default clause for when we do not really find the right target. And why is inline cache a speculative optimization? That's because we pay the cost of generating the inline code, and there is the guard around it, which is executed whenever we run over that code. But if this code is not the most common target of the dispatch, then our optimization will backfire, because then the program will slow down a bit. But there are many studies about the effectiveness of inline caches. So a hit in a monomorphic inline cache finds the target of a call with about 10 instructions in JavaScript v8. That's a result from 2014, published in PLDI. If we have more types, say 10 possible targets inlined, then we need more instructions, like 35 or so. But if we miss, then we need more than 1,000 instructions to locate the right target. And that was inline caches. That's possibly the most well-known and applicable optimization in the context of dynamically typed languages. In the next class, we shall talk about other types of optimizations for JIT compilers. In particular, we'll be talking about value specialization. Thank you.